Hi everyone, I'm Asta Yadav. Welcome to the session where we'll dive into Algorand smart contract development. In this part of the series, we will explore how to build a personal bank smart contract, a simple yet powerful example to understand the fundamentals of a decentralized application on Algorand. We'll be using Algorand Typescript, which allows us to write and deploy smart contracts in a language that is familiar to many web developers without having to learn a completely new syntax. Throughout this session, I'll walk you through each and every step from setting up the project environment to writing the smart contract logic, deploying it on a local sandbox network, and finally testing it visually with Lora. By the end, you'll not only have a working smart contract, but also a clear understanding of the development workflow, best practices, and how Algorand makes blockchain development approachable and efficient for developers of all levels. Our goal here is to create a decentralized personal bank application where users can deposit and withdraw algo securely on chain. Here's what our personal bank will do: it will accept deposit from users, track each user's balance securely, allow users to withdraw their full balance, all while being completely decentralized and trustless. At the end of this section, you would have built a fully functional personal bank smart contract, learned Algorand's powerful development workflow, deployed your contract on a local network, and used visual tools to interact with your smart contract. And the best part, everything we built today uses TypeScript, so you don't need to learn a new programming language. Now, before we start coding, let's make sure you have everything you need. If you don't have these, I would recommend you to go back to the previous installation section and come back once everything is installed. Let's go to the terminal and check if we have AlgoKit installed. AlgoKit is Algorand's comprehensive development toolkit. We will verify it using the command AlgoKit version. It shows 2.8.0 for me, but if you are seeing it later, it should be an updated version for you. Great, now let's start our local Algorand network. LocalNet is a private sandboxed environment for testing smart contracts without using real algo or interacting with mainnet or testnet. You don't need to create accounts. It gives you some accounts and algos as balance. Now, LocalNet helps us to verify functionality quickly. In case you want to check whether your LocalNet is up and running, you can use AlgoKit LocalNet status. You will need Docker installed to run LocalNet. So if you haven't done that, I would recommend you to do that. And then come back, and then you can hit the command to start the network, which is AlgoKit LocalNet start. Now, once you have done that and it's up and running, that's great. And it will show you as running status. But if not, you'll have to check your Docker and go through the steps to debug it. Now, if you are already using LocalNet from some time and you want to reset all the accounts and balances, you can do that using the command AlgoKit LocalNet reset. Cool. So now let's clone our workshop repository. You can find all the links in the description. We'll go ahead and we'll write git clone and then paste our URL. Now, once we have cloned this, we'll navigate to the project and you can open it using your editor. I'm using Cursor, but any ID should work. So we'll go ahead, we'll enter into Algorand TypeScript workshop folder. Now, before moving to the structure of the project, let's install all the dependencies of this project so that we don't have to do it manually later on. For this, we will use the command AlgoKit project bootstrap all. Now, this might take some time depending on your internet, but I think we should be good to go in a few seconds. Now, let's go through the project structure quickly. Now, this is an AlgoKit workspace, which is a powerful way to organize multiple related projects. So all your related projects can live under one root directory and share, for example, all the common settings that are inherited across sub-projects. So for example, if you have different folders for smart contracts, for front-end, etc., they all can come and be under one root directory. And it also provides optimized tooling, which is perfect for if you have VS Code integration and helps you in CI/CD setup as well. Now for this, you can go to .algokit.toml file, workspace root. Inside the projects folder, you can have multiple sub-projects and that would be listed over here. And maybe, for example, as I mentioned, a smart contract, a front-end, etc., and all of that would work together. You can click on Open Workspace and it will open the workspace for you. Now let's explore what we have inside AlgoKit project. we have a contracts folder, which is our main folder wherein our smart contract lives. And also we have our deployment file and test files. We also have an artifacts folder, which is the folder which is used once we compile a smart contract, and will generate all these files after compilation in the artifacts folder. So whether you're building a simple contract or a complex project, this structure keeps everything clean and manageable. Now let's check out the contract flow. Now in this contract, we have two functions. First is the deposit, where users send algos to our contract. Second is the withdraw function, where users can retrieve the full balance anytime. We also use storage to track each user's balance in secure box storage. Now let's go through this line by line. First, we will add imports from Algorand Typescript library. Here's what we will import. So first is the ABI method, which is a decorator that marks a function as callable from off-chain clients or from other contracts using ABI, which is application binary interface, which defines how your methods will look like, what will be the return parameters, if it's returning something. Now, it also allows you to specify whether the method is read-only or other things. So you can specify a lot of things over here in ABI method. Now, next is account, which represents an Algorand account. It is used to retrieve account data and as a parameter type in ABI methods. Now, assert is used to enforce conditions within the contract logic. So, for example, if the condition fails, the transaction will be rejected. Next, we have box map. So, this is a key value storage system, which is on chain for storing your contract data. We have looked at different types of storages in our previous sections. So we'll not go through that again. But here we are going to use box storages. Now with the common key prefix and value type, we can use these boxes, and it's helpful if you're storing per entity data or per account data efficiently in box storage. Now next we have is contract. So this is the base class which we use for creating Algorand smart contracts in TypeScript. All contract classes should extend this. Next is global, which provides values for applications or current transaction, like, for example, current application address, group ID, or creator address. Now, group transaction. This represents a group of transactions with an atomic transaction group. If, for example, we want to call a payment transaction, and that we are going to look at it in a while. And if you want to send it along with a contract call, we can do that totally using group transaction. Now, inner transaction, which is ITXN, this is used for constructing and submitting inner transaction, which are transactions executed by the smart contract itself. So it would allow contracts to create payments, to create asset transfers, or even application calls as part of their execution. So next we have is transaction, which represents the current transaction calling the contract, and it provides access to properties like senders, like arguments, and transaction type. So there are a lot of transactions that we can do. There are, I guess, 16 different types of transactions that we can do. Then we have UN64. This is a data type representing AVM's native 64-bit unsigned integer, which is used for amounts like, for example, algos. Now, once we have imported these, we start with our code, wherein first of all, we export our class and we call our class as personal bank. So this creates a smart contract named as personal bank, and it makes it available outside the file. And it extends contract, which means that it inherits from the base contract class, which gives it access to all smart contract functionality. We declare a public storage variable and we name it as depositors. In this box map, so this contains this account and UN64. So this stores as key value pair, wherein the key is an Algorand account address, and the value is equal to the amount that account has deposited, which is a UN64. Now we write a key prefix over here as depositors because prefix is used for storage of keys to organize data. Now, before writing deposit and withdraw functions, we define ABI methods. So this makes deposit function externally callable. So this means that we can interact with deposit function using visual tools, for example, Lora, that we are going to see later in this section. Now we have a deposit function. Now we have defined a parameter as pay transaction, which is a group transaction. And this defines a function that would accept a payment transaction as input. Now, in this function, we write assert, basically enforces rules. So, first is that the payment must be sent to the contract address, and the deposit amount should be greater than zero. So, this is done so that if there is any transaction that is of zero value, or if it's not sending it to contract address, then we fail it immediately and we don't proceed to the next steps. Now, next is that we have deposit amount, and this stores how much deposit is being deposited, checks whether the account already has a previous deposit stored or not. Now, if account already has a deposit, we add it to the existing balance so that we maintain all the balance of one account at one place. Now, if the account hasn't made any deposit previously, we set the balance to deposited amount. Now, this returns the updated balance to confirm how much the account now would have. Now we have a withdraw function. So this one also has ABI method decorator so that it can be called externally. Now withdraw will withdraw all the funds for the user. Now here we have added a maybe, which checks if an account has stored value and returns deposited amount, which is how much they have deposited, and is deposited checks whether a deposit already exists or not. Now, here we have defined assert, which ensures that the account has funds to withdraw. And if, for example, we have all these asserts checked and it has been successful, then we create an inner payment transaction when the receiver is the person who is calling and who has that particular balance. And it will send back all the deposited amount that it has from the user. So that means that the user can withdraw these funds. And the amount is the full deposited amount. So even if, for example, first we send 2 algos and then we send 10 algos, then once we are withdrawing, that time we will withdraw 12 algos, which will be the total amount that particular account has deposited. And the fee has been set to 0. Now, next is that we've written as submit, which would execute the payment and it would reset the user's deposit to 0 since the withdrawal has been made. And then in the end, it would return the withdrawal amount for confirmation. Now that we have completed our smart contract logic, let's compile a contract to see what AlgoKit would generate. So we would use the command AlgoKit project run build. And we can also add personal bank. So we are adding this personal bank, which is optional but helpful in case you have multiple projects. So if you have only one project, you can skip it as well. So let's check the artifacts folder now. AlgoKit has generated several important files. So the first one is personalbank.approval.teal, and we also have .clear.teal. So these are the files that contain the actual bytecode that runs on Algorand. So teal stands for Transaction Execution Approval Language. So this is where our TypeScript compiled down to. You don't need to read teal, but seeing how our high-level TypeScript becomes low-level blockchain instructions is definitely fascinating. Now, the .puya.map files are really helpful for debugging code. They map our compiled bytecode back to the original TypeScript. So when you're debugging in VS Code, you can step through your TypeScript code even though your blockchain runs teal. Next, we have arc specification files, arc32.json and arc56.json. So these are application specifications, and arc56.json contains even more metadata than arc32.json. So they describe our contract's interface, including what method it has, what parameters they take, etc. These are useful when we deploy or even if you want to interact with Lora, which we'll discuss later on. These specs enable tooling integrations and other developers can understand your contract's interface without reading your source code. Lastly, we have personalbankclient.ts. So it's a fully typed TypeScript client that interacts with a contract. Now that we have successfully compiled a smart contract, let's go to the next step, which is deploying a smart contract. Now with AlgoKit, we have deployment script already ready, and we just have to make tweaks according to our new logic of our smart contract. Now, in summary, the script uses AlgoKit utils. To create an Algorand client from an environment, grabs a deployer account, which is auto created on localnet if needed, builds a typed app factory from your compiled contract client, deploys the app, optionally funds the app with one algo, and prints the deployment details. So let's check this script line by line now. First, we'll import Algorand client, which is a helper wrapper that helps us to connect to different networks. Example, to localnet, to mainnet, to testnet, etc. And it does that using the environment variables that we specify. Next, we will import personal bank factory. This is the auto-generated type client for our compiled personal bank contract. And this is the reason why we compile it before we deploy it. Now, inside the deploy function, we initialize Algorand client. If no environment variables are provided, like in our case, which is typical for a local dev, it falls back to localnet settings provided by AlgoKit. We also define the deployer account, which we again take using environment variables that we have defined. For localnet, it uses key management daemon, which we also call it as KMD, which will create an auto-funded account. So we name this account as deployer. Now the deployer contains address and methods to sign or send transactions. Next, we use get typed app factory, which builds a helper around your compiled contract. For example, the personal bank factory. It knows how to create, deploy, update instances of your app, and provides type clients for calling ABI methods. Here in default sender, we have to set it to deployer.address, which means that it sets the default transaction sender for factory actions. So the deployer will be the creator by default. Now, console log basically prints a message to the console, including the app name from the typed factory. Now, this is an important line wherein typed factory.deploy actually deploys the application to the network. There are different options over here. App name, which is the name for a deployment. On update append is used if code changes, for example, later. We prefer creating a new app instead of modifying the existing app. So this can prevent accidental changes on the same app ID while developing. We also append on schema break, which is, for example, if you change storage schema, we want to create a new app ID rather than failing or updating in the same place. Now we also have kept suppressing log as true, which is basically you can adjust if you want more output or not. Now this will return app client, which is a typed client bound to your deploy app instance, which is useful for later calls. Now it will also return result, which is metadata about the deployment operations, including operation performed, transaction IDs, etc. Now, after deployment, the code checks whether the deployment was created or replaced in app. If yes, it sends one algo from the deployer to the app address to ensure that the contract has enough balance to pay minimum balance and transaction fees. Now, one.algo is a helper that converts one algo into microalgos, which is the atomic unit that we have. And this is a convenient like shorthand used by AlgoKit utils. Next, we just destructure common fields from the app client, which is app ID, app address, app name, etc. So app ID is the numeric ID on chain. App address is the escrow address, and we have the app name. Now, console.table in the end would print a neat table so that you can quickly copy the app ID or address to use in tests. Okay, now that we have gone through our deployment file, let's deploy it to localnet. We already discussed about localnet and how to start it in the beginning of this section. So ensure that your localnet is up and running. To deploy localnet, we are going to use the command algokit project deploy localnet, and we can change it from localnet to testnet or mainnet once we move to those stages. If we have multiple projects, we can also add an optional personal bank. So we only deploy personal bank's smart contract and we don't deploy all the other contracts. Now let's analyze the output. It shows that it has deployed personal bank on application ID 1002. So this is unique when we deploy a contract and it helps to identify a deployment. So you should make a note of this and you should store the ID somewhere. Now, the next step is to interact with the smart contract using Lora. So, Lora is a powerful web based visual tool, and this is designed to streamline Algorand's local development experience. It acts as both as a network explorer and a tool for building and testing Algorand applications. Now, to access Lora, we can either run command algokit explore or we can directly go to lora.algokit.io. Here, as you can see, we can connect to any network. For now, we will connect to local net. Also, we have a wallet connect option. I have connected using Loot, but you can connect to any other options that are available to you. For example, if you want to create a new account, you can create it over here. If you don't have balance in your account, then head over to the Fund tab and enter how much amount of algos you need for testing on localnet, and you will instantly receive these test algos. Now that we have enough funds, let's head over to AppLab. So AppLab helps us to deploy, simulate, and call smart contracts by uploading Arc32 or Arc56. Now we have two options. One is to deploy from here itself, but since we have already deployed it before using algo deploy command, we can use already existing app and enter the app ID we got when we deployed using the deploy command. Now it was 1002 for me. So let's go ahead and now upload arc56.json. You can upload arc32 as well. So you can just enter the name and that you want to see over in AppLab. And it should be a unique one, not the others that are currently there in your AppLab. So now we'll test our smart contract functions like withdraw and deposit through AppLab. Now, once we hit on create button, we can see the application available over here. So let's go inside the application now. Here you can see a bunch of details about it. Example, account address, which is the account that holds algos and ESAs, pay transaction fees, especially for any transactions, send and receive transactions as part of smart contract logic. So one algo that you sent during the deployment file, this is the account that holds it and has to take care of the requirement of minimum balance. Below this, we see ABI methods. So these are the methods we defined in our smart contract logic, which has deposit and withdraw. And now that we also see state, so this is where we can see storages, which is local, global, and box. So any changes that we do and would affect storage, we can see over here. Now, in this contract, we used boxes to maintain the balance of users. So we'll check box state once we execute a deposit method. Lastly, in the end, we can see all the live and historical transactions happening, and we can go ahead and check out these transactions in details by clicking on one of them. Now, let's start with deposit function. In this one, we can click on call. It shows us all the details to build the transaction. We can keep it as it is. Now, since we have only one argument, which is a payment transaction, wherein we are depositing some amount to this smart contract. So for that, we'll copy the contract address of this application, and now we'll click on payment transaction and add this address in the receiver. Let's enter amount as 2 algos. Now, before we click on send, we need to click on populate resources. It does the automatic detection and inclusion of required resource references. For example, we have accounts, assets, applications, and boxes when we are preparing and sending smart contract transactions. Now, it basically ensures that all the necessary references are included in the transaction, and if we don't use it, we would end up in a failed transaction. So now we click on send button, and we can see visually that an amount of 2 algos has been sent to the smart contract account. We can also click on this transaction ID and see all the details of this transaction. You can see the tags like application call over here. In the code, we are using boxmap to track all the deposits. So now let's go to box state, and we will see a box created over here. Before we go further, let's again call the deposit function, and let's say we are depositing 10 algos this time, so that we can verify whether it's returning all the deposited amount or not, which should be 12 algos now. So we go through the same steps and we populate resources again, and let's hit the send button. Okay, we can see that the first one is our wallet address, and after the arrow is the application's account address. Now let's go to the withdraw function and let's click on call. Here we should just update our transaction fee, since a little bit extra of transaction fee would be used. Now the reason is that one who calls has to pay for the inner transaction fees. Let's call now populate resources and click on send. Okay, great, it's successful. Now we can see the balance has been reduced from the application's account, and it gets credited back to our account. We also check whether the box map has been updated or not. Now we have successfully executed deposit and withdraw functions. All right, let's do a quick recap of what we have built in this session. We have created a fully functional personal bank smart contract which is complete with secure deposit and withdraw features. We used box maps for persistent storage. We have set up a full deployment workflow, and we have even tested everything visually with Lora. Pretty cool, right? So, what are the big lessons from today? First, you don't need to learn a whole new language to build on Algorand. We have Algorand Python and Typescript for that. Second is developer experience. Algorand gives you world-class tooling that makes process smooth. Third is the visual development, wherein Lora makes testing feel natural and intuitive. And finally, type safety for auto-generated clients. That really helps you move faster with fewer errors. Now, before you hit mainnet, a few things to keep in mind is always test it before on local intent testnet to catch those edgy cases early. For unit tests and end-to-end tests, do check out our next section of the video. Also get a proper security audit, manage your keys carefully. If you're excited to keep building, your next steps should be to check out the full developer documentation. It's packed with guides and examples. Join our Discord community. There are lots of great developers there to learn from and collaborate with. And don't miss the workshops. We go into applications and best practices. Thanks for coding with me today. Can't wait to see what you create next. Thank you.